Good morning, class. Today we're continuing with CPU scheduling. Here are today's topics, and to keep them fresh in your memories, the objectives for this chapter. Okay, thread scheduling. To review, given the confusion you had as shown by the kernel level and user level threads question on the exam, kernel level threads are known to the kernel for scheduling purposes, but do not necessarily run in kernel mode. They'll typically be running in user mode. User level threads are not known to the kernel, so they're scheduled by the user process using the thread library. So the second bullet here, when threads supported, threads scheduled on processes refers to kernel level threads. The third bullet refers to user level threads that are multiplexed on lightweight processes, which is often an abstraction level between user level threads and kernel level threads. So these threads contend for CPU cycles at the process level, so they're not competing directly against other threads, and prioritization is done by the programmer. Kernel threads, because they are scheduled by the kernel, and the kernel has the scope of the entire system, are contend at the system level among all the kernel threads. So under some circumstances, the Pthread library does permit user specification of the scoping level, but we won't be getting involved with this level of detail. And again, I'm going to skip over this. Skip this. All right, so when we have a multi-processor system, whether multiple CPU chips or a single CPU chip with multiple cores, or multiple CPU chips with multiple cores, CPU scheduling gets more complicated because now we have these independent processors that are accessing shared data structures, so there's synchronization involved. So we're assuming that all the processors are the same, hence homogeneous processors. In asymmetric multiprocessing, a single processor handles the scheduling for all the processors. That's simpler in some respects, but then that single processor can become a bottleneck. In symmetric multiprocessing, each CPU handles scheduling on itself, but again, synchronization comes into play. Processor affinity refers to the ability of a process to move between processors. So soft affinity means that a process will move infrequently. Hard affinity means that a process is permanently bound to a particular processor. This can be advantageous to prevent overhead when a process starts up. If you think about the caches that are associated with CPUs, if a process moves from one core to another core, it's going to suffer a large number of cache misses until the cache warms up and becomes loaded with the process's memory, active memory. NUMA is an acronym standing for Non-Uniform Memory Access. This is a specialized memory architecture in which not all of main memory can be accessed at the same speed as other parts of memory. So in this example, main memory is somewhat bound to CPUs. And the memory bound to a particular CPU can be accessed quickly, whereas memory bound to another CPU is accessed more slowly. This is another situation in which process affinity would come into play. So in addition to the CPU scheduler accounting for affinity, the CPU scheduler should also account for balancing the workload among the processors. So, for example, you wouldn't want all the CPU-bound processes to be running on one CPU in a 2 CPU system when all the I/O-bound processes are running on the second CPU. You'd want to balance that workload between the 2 CPUs that you had. And as mentioned, here there are there are 2 strategies: push migration and pull migration for affecting load balancing. So to try to hide memory latency, because a CPU can be forced to stall if it gets a cache miss and has to go to memory, we're seeing process state or architectural state on processors being replicated so that a processor can switch between threads. This technology is known as hyperthreading in the x86 architecture, so that if one thread incurs a cache miss and is going to suffer memory latency, the CPU can simply switch the registers and the control state that it's using and run another thread for some number of cycles until the first thread has its memory request satisfied, or that second thread takes a cache miss. So here's an example. In this illustration, the CPU is only being used half the time, as you can see, because it's switching back and forth between compute cycles and memory stall cycles, during which it's just sitting idle. A threaded processor, such as a hyperthreading x86 processor, will simply switch between the 2 threads, and of course this is an idealized illustration, but it demonstrates that the CPU utilization is much higher with hyperthreading. So I'm just going to touch on real-time systems briefly. In a real-time system, there are deadlines by which an external event needs to be responded to. So in a soft real-time system, there are no guarantees when that response will be completed. All that we know about a soft real-time system is that the event process will be given a higher, perhaps the highest priority. In a hard real-time system, there are guarantees with respect to when an event process will be completed. If you think about it, making those guarantees can be tricky. So the operating system has to take into account its current workload, and when it's evaluating whether to admit a new process or not, it has to make a decision with respect to whether it's going to be able to maintain all of its hard deadlines. Okay, this timeline illustrates an event occurring and the completion of the event process. So the event occurs, some amount of time is required for interrupt processing. Then we have to free up all the resources needed by the process and then perform the context switch to the process. Then the process executes, and finally we've completed the response to the event. So some of the characteristics we're looking at in real-time systems are: we have events that occur at certain periods, deadlines that are less than the time of the period, and then the processing time for the event process itself. Rate monotonic scheduling is one scheduling algorithm that's used for real-time systems. So as it says here, that it's priority based, and the priority is based on the inverse of the period. What you might remember from CS311L13 and looking at clock rates and clock frequencies, the the clock frequency is the inverse of the period, so we can look at this as an event that occurs more frequently has a higher priority. As illustrated here, process 1 is being triggered twice as frequently as process 2, so process 1 has a higher priority than process 2, as demonstrated here. When the next event for process 1 occurs, process 1 preempts process 2, and it's not until process 1 completes that we resume process 2. This can result in missed deadlines as illustrated here. Process 1 completes, and then in preparation for the deadline for process 2, we start executing process 2, but then the event for process 1 occurs. So we preempt process 2, run process 1, it completes, we resume running process 2, but it doesn't complete by the deadline. Of course, the problem here is that we have the slack time here, during which we could be finishing up process 1, allowing us to slide process 2 this way, but that's not the way rate monotonic scheduling works. So this is a flaw with respect to rate monotonic scheduling. And then this is a situation where the timing of the process is such that we have a sufficient number of CPU cycles to handle these hard deadlines. It's simply that we're not scheduling the processes in the correct manner. All right, so earliest deadline first scheduling is an improvement over rate monotonic scheduling. So the process that has the closest deadline is given the highest priority. So in this example, we see that process 1 finishes up. It has the highest priority because its deadline is the soonest. Then we start process 2 and allow that to complete, even though the next event triggering process 1 has occurred. So process 1 is back in the ready queue, but we don't preempt process 2 because it now has a higher priority because its deadline is closer. I'm going to skip this. I'll also skip this, and skip this. Okay, so that finishes up the second screencast on CPU scheduling.